A quantum computer is not just a faster version of the one you have on your desk. It's a machine built on entirely different physical principles, capable of tackling problems that would take a classical computer millions of years to solve. Instead of bits that can only be a 0 or a 1, a quantum computer uses quantum bits, qubits, that, thanks to the laws of quantum mechanics, can exist as both 0 and 1 at the same time in what's called superposition. This means that a single qubit can represent many possible states simultaneously, allowing a quantum computer to perform massive numbers of calculations in parallel. Another key feature is quantum entanglement, a phenomenon in which the state of one qubit is inseparably linked to the state of another, even if they're separated by vast distances. In practice, this means that changing one instantly affects the other, enabling quantum computers to process information in ways no classical processor can replicate. When combined with superposition, entanglement makes it possible to design quantum algorithms that narrow an enormous space of possibilities down to the single correct answer. One of the most famous examples is Shor's algorithm, which can factor huge numbers into their prime components far more quickly than the best classical methods. In real terms, that could break widely used encryption systems like RSA. Another is Grover's algorithm, which can search an unstructured database significantly faster than classical searching. These abilities are why quantum computing is discussed not only in scientific circles, but also in the worlds of cybersecurity and national security. Building a quantum computer, however, is not as simple as writing new software. It's an extreme engineering challenge. Qubits are incredibly sensitive to their surroundings, and any interaction with heat, electromagnetic noise, or vibrations causes a loss of their quantum state, a process called decoherence. To avoid this, today's quantum processors are placed in cryogenic systems and cooled to temperatures near absolute zero, around -273 degrees Celsius, minimizing noise and extending the time qubits can remain quantum. There are several major approaches to building qubits. Superconducting circuits use electrons that flow without resistance, controlled by microwave pulses. Ion traps hold individual ions in space with electromagnetic fields and manipulate them with lasers. Photonic systems use single particles of light and their quantum states. Each approach has its own advantages. Some are faster, others more stable, but none are yet perfect or easily scalable to the millions of qubits needed for a universal quantum computer. Today's quantum machines fall into the NISQ category, noisy intermediate-scale quantum. They have tens or hundreds of qubits, can handle only a limited set of tasks, and are prone to errors that must be corrected with complex quantum error correction codes. Still, even in this noisy and limited form, they're already finding use in simulating molecules, optimizing complex systems, and helping design new materials. In these areas, they can work directly with quantum effects that classical computers can only approximate, which is why they can deliver more accurate and sometimes faster results. Quantum computers are not a universal solution to every problem. In many areas, classical algorithms will remain faster and more practical. The real advantage of quantum computing lies in solving specific types of problems, those where parallel state processing and probability interference can dramatically speed things up. To make that happen, we need entirely new algorithms designed from the ground up for quantum processors. Perhaps the most exciting part is what quantum computing could mean for the future of science and technology. It could accelerate the discovery of new drugs, help design more efficient solar cells and catalysts, model climate change with unprecedented accuracy, and uncover materials with properties that today seem impossible. While quantum computers are still found only in the labs of major tech companies and research institutions, their very existence shows that computing doesn't have to be forever limited by classical bits and transistors. They prove that information can be stored and manipulated at the level of individual particles, and that the physics governing this level opens doors to forms of computation we once thought impossible. A quantum computer is not just about speed. It's a new way of thinking about problems, a new way of finding answers, and a new way of working with information. It's a technology that blends the strangest aspects of quantum physics with the most practical side of engineering. And if it succeeds, It could change how we understand computing power, security, and scientific progress. The future may belong to those who can merge mathematics, physics, and technology into something that, today, looks like magic. And quantum computers are proof that this kind of magic has already begun to become reality.